The last part of our discussion on filters concerns active filters. Active filters are created using passive elements as before and op amps. We can use inductors. We don't often because they're big and bulky, and op amps are small. And one of the nice things about active filters is they don't have a great deal of size. So, advantages we have when we deal with active filters. One, we can actually have a gain. We can actually amplify the signal. Passive filters, because they're basically circuits, always make the signal smaller. They can't ever make the signal bigger. So if we need to make a signal bigger, an active filter will actually do that. Also, if we add a load, a resistor, or some other kind of load, it doesn't affect the circuit. So we can design the filter and have it respond a certain way, and then adding something to it is not going to change the characteristics of the filter. They're smaller in size and weight. They don't cost very much, and there's a great deal of flexibility in how they can be designed. There's actually one can actually study an entire course on just active filters. There's tons and tons and tons of kinds that can be used. Disadvantages, you have to have a power supply. They have to be powered by a DC power supply. Obviously, passive filters don't need a power supply. They can't process signals outside the DC power supply limits. So that's why they can't do really large voltages or large currents, because they're small powered devices. So for very big signals, they don't work so well. They also have issues at high frequencies. Once the frequency gets up to a certain point, the op amp actually starts to attenuate the signal, and so beyond a certain frequency, they don't work so well. So we're just going to look at two kinds. We're going to look at the first order low pass filter and the first order high pass filter. And first of all, we're going to start with something that you already know, which is the inverting gain op amp circuit. This looks a little bit different than the one that you're used to. The only real big difference is now, instead of resistors in the feedback path and in series with the input, we actually have impedances. So this is exactly the same circuit that you looked at when we studied op amps. The only difference is now we have impedance values. This is actually a more general form of the inverting op amp circuit, and its gain is also in a more general form. We just take minus Z2 over Z1, so it actually follows the same basic format as the inverting op amp circuit of before, only now we have impedances instead of resistances. So, for the low pass filter, we use a resistor and capacitor in parallel for Z2. So there's actually a capacitor and a resistor, both in the feedback path. And then we use a resistor for Z1. So when we come up with the gain, or the output versus input, the transfer function, Z1 is just going to be R1, that's easy. And then Z2 is going to be R2 in parallel with 1 over j omega c. So we multiply the two together, and we add them on the denominator, and with a little algebraic manipulation, we get R2 over j omega R2c plus 1. So, since V out over V in is minus Z2 over Z1, all we do is plug in those values. We take V out over V in, and then what's been done is the R1 is just minus 1 over R1. It just makes the manipulation of the algebra a little easier. And then we put Z2 in its original form. And then what we're going to do is pull out R2 from the second part of the equation. And there is reason for that. And the reason for that is that this is the low frequency gain. And it should look familiar. This is the gain you get with a regular inverting op amp circuit when you do not have a capacitor. And at low frequencies, the capacitor impedance is such that it looks like it doesn't affect the circuit, and basically that whole thing just becomes 1. So, that being said, we're going to go on and figure out how we find the break frequency. Like I said, we're not going to worry too much about the magnitude of the gain. We're going to worry more about the actual break frequencies. The only part that we actually use with this is we do use the low frequency or the high frequency gain to make some adjustments and calculations, but we don't use the whole transfer function. So, how do we find the break or half power frequency in this particular type of circuit? It's a little bit different, but it's not terribly different. We do need to find the magnitude of the gain, but we're not really going to use it for much. Then we're going to set that equal to 1 over square root of 2 times that low frequency gain, because that's sort of part of the gain. So when that happens, we take R2 over R1, and the negative went away because we're dealing with magnitude, so we don't really care what the sign is. And then we have 1 over the square root of omega R2C squared plus 1 squared, and that's going to equal R2 over R1 times 1 over square root of 2. And you'll notice that that R2 over R1 is on both sides, so we can actually eliminate that. And when we do, we basically get the same thing that we got with other circuits when we were dealing with passive filters. We get omega R2C squared plus 1 equals 2. So we basically get omega R2C equals 1, or the break frequency equals 1 over 2 pi R2C. So R2C are the two elements that are interacting to create the break frequency. They are physically closer together, they're physically connected, they don't have the op-amp kind of between them, so their interaction produces the break frequency. R1 actually has no effect on the break frequency whatsoever. So when calculating the break frequency for an active low-pass filter, we actually only use R2 for that value. So what would we do if we wanted to actually design? Because these are actually pretty easy to design, these filters. So let's say we want an active low-pass filter, and we need to use standard resistor values just because that's the only thing that we have available. And we want a low frequency gain of 20 dB and a break frequency of 10 kilohertz. If you are not given a value of one of those components, you're kind of stuck, or you have to make one up. So oftentimes we set the capacitor value to a certain value because there are many, many more resistors available than there are capacitors available. So we have set the capacitor to 470 picofarads, and then we go from there. And it's not a very difficult process. Since we know the frequency we want and we know the capacitor value, we can use the break frequency formula to figure out what R2 should be. So we're just going to switch the break frequency in R2 in that equation, and when we do that and calculate out the value, we get 33.863 kiloohms. Yeah, it's not a standard value, but we'll deal with that later. We want to keep that original value for right now. Once we get that, we can find R1 because we've been given the low frequency gain. We do have to turn that from a decibel number to a number. So we're just going to take 10 to the 20 dB divided by 20, because since 20 log of 10, or the value would be equal to 20 dB, and we get a gain of 10, and that means that R1 is just going to equal R2 over 10, which is 3.386 kiloohms. Now that we have that, the next thing that we're going to do is we're going to convert R1 and R2 to standard values. And the closest thing we have is 3.3 kiloohms and 33 kiloohms. So let's test the circuit. We can use LT Spice. We don't have to go out and build it. This circuit actually has the power that's powering the op-amp over here, and it has labels that relate the voltage values over to the op-amp. And we're actually going to run an AC sweep from 10 hertz to 10 megahertz. And we've got all our component values put in. And when we do that, we get this output. You'll notice that the low frequency gain is 20 dB, which it should be. And then if we go 3 dB below that and go to where the trace intersects the arrow and then drop down, we get our break frequency, which is 10 kilohertz. So that's exactly what we would expect. So even though we had to use standard values, we still get very reasonable results from this particular filter. A high-pass filter is very, very similar. The only difference is that we have a resistor and capacitor in series for Z1, and then we just have a resistor in the feedback path for Z2. So we can go through and find, again, the value of Z1. We're going to add R1 plus 1 over j omega C and find a common denominator, and we get this kind of j omega R1 C plus 1 over j omega C. And then Z2 is just going to be equal to R2. So again, we take V out over V in, which is minus Z2 over Z1, and we get minus R2. So R2, remember, that's the value that's on top. And then next to that, multiplied by that, is the inverse of what Z1 is, because we're dividing by Z1. So we get j omega C over j omega R1 C plus 1. And now, in order to put it in the same format that we have the other transfer function in, we have pulled out 1 over R1. And so we've changed the transfer function a little bit. But again, now we have the high frequency gain pulled out and the rest of the transfer function set aside for its frequency dependence. So how do we find the break frequency? Well, this again is the same exact process we did before. We find the magnitude of the gain. We set it equal to 1 over square root of 2 times the high frequency gain. And again, the high frequency gains cancel out. And again, the results look exactly the same, except for the fact that a different resistor is used to find the break frequency. So this time, omega R1C is equal to 1. So the break frequency is 1 over 2 pi R1C. And that's because those two values are physically connected in the circuit. Because they're physically connected, they are the ones that actually determine what the break frequency is. The interaction between R1 and C produces the break frequency. This time R2 has no effect on it whatsoever. So, as a second example, we're going to design a high-pass filter, and we're going to, again, use standard values. We have a high frequency gain of 40 dB and a break frequency of 1 kilohertz, and we've been given the capacitor value, again, of 33 nanofarads this time. So the first thing we do is find R1, since the break frequency is related to R1 and C. We turn that equation around slightly, and we get 4.8.23 kiloohms for R1. Then we can find R2. The gain value this time is 10 to the 40 dB over 20, which would be 10 squared or 100. So R2 is going to be 100 times R1, which gives us 482.3 kiloohms. We then convert R1 and R2 to standard values, and the closest values we can get to those are 4.7 kiloohms and 470 kiloohms. And then we test the circuit. We go through, and again in LT Spice, we go through and make a circuit, and this is pretty much similar to the other one, and we run it, and we get the following response. The high frequency gain is 40 dB, which is good. And as far as finding the minus 3 dB point, we have an arrow going over to where it intersects with the trace, and then we drop down and we get a break frequency of 1 kilohertz. And that's awesome, because that's exactly what we designed it for. There is, however, one problem with this circuit. You'll notice that I didn't go very far into the high frequency realm, and there's a reason for that. If I were to extend this simulation up above 10 kilohertz, and actually I'm going to extend it out to 1 megahertz, something happens, and this is why we can't always use active filters, especially at high frequencies. When we extend it, the gain rolls off, and it rolls off pretty quickly after 10 kilohertz. It drops pretty dramatically. And that is that high frequency limitation of the op-amp. So even though we can make a high pass filter, we have to use that at low frequencies in order for it to work. So that's the overall coverage of active filters we're going to do. There's plenty more, but we're not going to cover that in this class.